Good evening. Hi. Yay. Hands up if you don't enjoy audience participation. Good. Can I have a graphs yay? Graphs yay. Louder. Yeah, all right. I've seen someone kind of give a whole kind of exercise just to get the audience up and running at the beginning of a conference talk, and I could never do that, so that's the closest I'll ever get. So thank you for the enthusiasm. So, who am I? I've been working on PHP for better, for good, and people have been paying me since 2004. I've written some horrible code in that time. I've written some less horrible code in that time. I've built some big things and some small things. I'm currently a senior software engineer at Datto. We do backup devices and cloud and virtualized backup things and whatnot. If you want to hear a story about Hillary Clinton, talk to me afterwards. Formerly at DataSift, where I was reading all your tweets and your Facebooks and your LinkedIns, and at Time Out Digital, where I was telling you what to do in London and Paris and stuff like that. I'm also the founder and co-organizer of PHP Berkshire, so if you ever fancy coming along to Reading on the third Wednesday of every month, because we decided we'd try not to clash with anyone around, please do. We're just up the M4. We're always after new speakers. If you want a 20-minute slot, we're really good for just saying, yeah, we'll throw you in. So please do come along and get some more Dominoes and some more beer and cider and soft drinks. So I also act. I also shave, and if you've seen me before, I also reuse my jokes. So there we go. That's what it looks like underneath that. Graphs are everywhere. So I'll apologize now. There's not much code. In fact, you're not going to see a line of code in this unless you count SQL. I'm just going to go through the basics of what graphs are, give you a couple of fun applications of them, and hopefully make you start thinking of how can I apply that to what I do in everyday work. When I say graphs are everywhere, you can look at the way this is built and say, well, there's a graph in the ceiling. We've got nodes or the tiles, and then between them, we've got the edges and so on. So we can look at many things in the physical and in our conceptual worlds and map them in the way that I'm about to go forward here. So hopefully you pick up something off this talk. If not, leave me feedback on Joined In, but make sure it's 5 stars so I can get more gigs after this, yeah? Cool, thank you. So first off, who's heard of the 7 bridges of Königsberg? Cool, so I'm not going to get it wrong for you people. Everyone else, this is the perfect explanation. So a guy called Leonhard Euler, or Euler? Yeah. It's a bad joke, that one. In Prussia in 1736, I guess. He was living in Königsberg. It's now Kaliningrad, but it's built around the Pregel River. And what you can see is we've got 4 main land masses. We've got the north side, the south side, the east side, and an island in the middle. And between those parts, we have bridges. And one thing he was thinking, as a mathematician, philosopher, was thinking, can you walk through the city, crossing each bridge only once? Can you visit every bit while crossing each bridge just the once? So if you cross over it, can't go over it again. So, being a philosopher, he thought, well, hang on, how can I boil this down to ideas and stuff? So he realized that the different land masses, the way they're shaped, doesn't actually matter. It's just the fact that there is a landmass, and there are the connections between. So all we need to do is kind of boil it down to what we're now starting to think of as graphs. So he was the father of graphs. And so what we have in a graph, we have nodes or vertices, and these are kind of solid points in whatever data you're storing, or maybe any conceptualization of the physical real world, anything like that, your land masses. And between them, we have edges, the connections between them. And these can be conceptual or maybe a bit meta, anything you like, something that basically says that this is connected to this some way. So here we've got north, south, east and central connected by the bridges. Now each of these nodes has a degree, and that degree is the number of connections that node has to it. So 3, 5 in the middle there, it's a very popular island, 3 and 3. So this is an example of an undirected graph. You can cross each connection, go between each node across each direction, whichever way you like. There's no kind of one-way system around the city, for example. If there was a one-way system, if you could only cross over this bridge in one direction, one over the other, we've got a directed graph. So we can say, to get from here to here, I can only use this connection in this way. I can't just kind of go back. So what Euler decided and determined and successfully found out is that you can't do this. Not in Königsberg anyway, in other places you can. And the reasoning there is, if you want to get into a node, you need one connection. And if you want to get out of a node, you need a second connection. So if you need to go to and then from a node, you need an even number of connections, an even number of edges. And therefore, the only nodes possible in that can have an odd number are the ones you either have to leave from first, so the start node, and the one that you arrive at the end, because you don't need to leave once you finish the end. And so, determine that only the start and end can have those odd numbers, that odd degree. And therefore, if you have a graph that has nodes where if you have a graph where the degrees of all the nodes are even, apart from 0 or 2 nodes where they're odd, then it will work. Otherwise, you can't kind of succeed there. And that was the way that Euler managed to determine whether he could walk around the city over all the bridges. History lesson, legacy, I'm on topic. So, pathfinding. That was an example of pathfinding. Wandering aimlessly around the city, crossing the bridges. When we come to graphs themselves, there are actually a couple of ways of doing that. How do you get from A to B? How do you get from, we'll see in a bit, Piccadilly Circus in London down to Trafalgar Square? So there are a couple of ways. How do you get from A to B, arbitrary node A, arbitrary node B in a graph? So there's depth first and breadth first, which hopefully is familiar to some of you, and if not, well, hopefully it's a refresher for you. So depth first, the first one. Basically, you follow the graph until you find the end. You just keep going. And if you find a dead end, you backtrack. So as an example, in this one here, we start at A, we go along the first connection we find. Next, oh, this is the next one we're going along. Great. And then we're back at A again. And this is an example of a cycle. So this graph is cyclic. It has cycles in, so you can go back and find yourself. And the best way of doing that is if you bump into a node you've already been to before, remember where you've been, and you say, well, okay, I'll consider that back at a dead end, and I'll backtrack from where I was going and try again from there. So in this one, we'll just keep wandering aimlessly around, randomly around, and when we get to a dead end, backtrack, go to the next one, backtrack, go to the next one, and we found B. And the worst case is that we get to the last node we're after last. We've just tried every single way around until we finally get to the end. That's the worst case, but yeah, we get there in the end. So a really good example of this is mazes. Now, the laser is not going to work on this screen, but how many people have solved mazes by, you enter the maze, you take the first turn on the left, and you keep going along and take the first turn on the left till you hit a dead end. Then you backtrack to where you made your last turn, take the next turn, and carry on and so on. It's pretty much that. So if you look at each intersection here as a node, and each path between those intersections, so, if right here we've got a node at the start, and then a node at this point where we've got branches here, you can kind of picture that in the same way of a depth-first search. So you hit a dead end, and you start going back to the last time you made a decision. If you can make another decision to go down another connection, you carry on that way. And as a result, you eventually follow everything through, backtrack, and eventually you get out. Kind of makes sense. Makes sense, cool. So you'll be solving mazes now with graphs, or thinking like graphs anyway. Sweet. Breadth first is the other approach here. And the idea here is you start from your same point and you go to every node that's one connection away. So have I got to B, have I got to B, have I got to B? No. Okay, so I haven't got there in one step. Now let's go to every node that's 2 away. Have I got to B? No. Have I got to B? No. Have I got to B? Have I got to B? This approach is still susceptible to cycles, but you can say, well, my third kind of iteration on that, I'll hit A, so I don't need to go down that path anymore and keep a memory of exactly where you are. But eventually, having checked everything 3 away now, we get to the end. We've kind of spread ourselves into the graph. We've gone to find the shortest path. The problem there then is, well, yeah, if you're doing a depth first search, you might get there randomly in 3 steps, but this we've had to check every single connection here to find our shortest path from A to B. But we can do some fun things like that with the 6 degrees of Kevin Bacon. Look at those eyes. Who's heard of the 6 degrees of Kevin Bacon? Cool, a few people. So, the 6 degrees of Kevin Bacon. You might have heard of the 6 degrees of separation. Kind of people investigated this on Facebook and whatnot to see how many people are connected to each other. But essentially, the Bacon number is the number of steps between them and Kevin Bacon via movies worked on by other actors. So, if actor A worked with actor B on movie 1, and actor B worked with actor C on movie 2, and actor C and Kevin Bacon worked on movie 3, then there's a Bacon number of 3 there. Or as a good example, Pierce Brosnan. What's Pierce Brosnan's Bacon number? Well, Pierce Brosnan was in After the Sunset. I haven't seen it. I assume it's not a great movie. We'll see how that goes. But it starred the late lamented Chris Penn, also in Reservoir Dogs, which is a much better movie, if you ask me. However, Chris Penn was also in the seminal classic Footloose, which starred Kevin Bacon. It's a fun thing with graphs. So you can kind of see this as connections between, nodes of Pierce Brosnan with a connection to After the Sunset, with a connection to Chris Penn, and the relationship there, the connection there, was in with. We've got some metadata about the connection between the two things there. Now, a graph to do that for IMDb, it'd be huge in memory. It's a pretty big deal. 3 million plus actors, 2 million plus movies and TV shows. Imagine doing that with a depth first search and just wandering around aimlessly via all sorts of stuff until you find Kevin Bacon. Imagine Kevin Bacon somewhere in the maze and you're just kind of digging in there. Have I found him yet? No. Have I found him yet? Dead end. Yeah. It can take a very long time. I mean, you might watch a lot of movies, but it would take a very long time. And that's where the breadth first type search comes in. You take the luck out of the equation. Yeah, you've got to process a lot of things there, but with a bit of caching, you can remember that Chris Penn has a connection to Kevin Bacon there, so you can forget any other connection there as soon as you've hit Chris Penn. And then for Pierce Brosnan, if you're working that out to begin with, all you have to do is find the path from that point on. And there's I think it's called the Oracle of Kevin Bacon, or the Kevin Bacon Oracle, where you can go online and you can hit refresh and keep finding different Bacon paths, I guess is a way of calling it. That sounds like a great path. Different Bacon paths to connect between a given actor that you choose and Kevin Bacon. An interesting approach to this kind of thing, though, is Dijkstra's algorithm. There's also A star, but I haven't a clue how that works, so I'm going to tell you what Dijkstra has to do with it. So, I mentioned Piccadilly Circus to Nelson's Column in Trafalgar Square in London. This is no fun on a grid kind of map, so I found something that is kind of vaguely difficult to pick your way through. How can we get from Piccadilly Circus to Nelson's Column? Well, we can do a breadth first search. Cool. Easy. How can we do it in the shortest distance possible? Right? So we can say how we can do it in the shortest connections possible if we model each intersection, like I was talking about on the mazes, if we say each intersection of roads is a node, and each bit of road between the intersections themselves are connections, or edges, we can easily go, well, we can find a route through there, just do our breadth first search, pan out until we kind of get there. But the problem is here, you've got bits of this graph which are short. Connections here in the real world are short and some are long. And so we might have to look at it and say, well, hang on, this distance here, this connection here is 2 units, or 1 unit, or 4. That's a big one for the map anyway. This is a weighted graph. So not only are we saying there's a connection between these two nodes, but we're saying that there's a cost to get between those nodes. And this is the kind of thing that Google's dealing with on a day-to-day basis when you say, how can I get from where I am to where I want to be? So Dijkstra's algorithm is a pretty good example of how you can use a breadth-first search to get from A to B. He did it with heaps, but we'll do it with graphs because we're crazy, or we're just me. So first off, all the nodes in your graph, in this very simple one here, we start off with infinite or null because we're in PHP land. Just mark them off like that. We know we want to start from the leftmost and we want to get to the rightmost. So our start one, we add a score of 0 because it doesn't cost us anything to get there. Okay? We see our weights here. We then visit each node connected to that one and give it a score equal to the node that you're on and visiting from, that score, plus the weight, the cost of getting to the next node. So in this example, pretty easy, 0 and 1 is 1. We can all do maths, and I haven't bored you to not be able to do maths yet. Cool. We then mark it as visited. And we take that approach and we apply it to each node that we've given a score. So we go to each scored node in turn and we go, what's the next node along? What other nodes can we get to? Take our current score, 1, add a weight of 2, we get 3. Take our current node of 1, add our score of 3, we get 4, or 1, and we get 2, and so on. Mark those as visited. And then we can work out there, well, hang on, we could get to this node, you'll see, start off at 4. But because we've got another connection to it from here, we visit this node of 2 here, add our 1, and, well, 3 is a bit less. So we can score it 3 away rather than 4, and so on. And finally, we get to the end. And once we've reached our end and processed all the unvisited scored nodes that we've already been to, we can say, right, now it's time to figure our way back from the end that we've got to. So we found our destination, but now we need to find the shortest distance from our start node to our end node. So what we do is we take our end node, this 4 here, and then we look at the nodes it's connected to, and we choose the node that has the smallest number when you combine the distance, the weight of that connection, to the score of the node. So we start with 4. 1 and 4 is 5, or 1 and 3 is 4, so go to 3. 3 and 1 is 4, 1 and 2 is 3. Well, we've got to go here because that's 3, and so on and so forth. And then we're at the end, and that's our path. We found our path all the way through. Has that made sense? Cool, I'm getting the job done. This is good. So yeah, if no nodes with a score are left, then we've gone everywhere we can when starting at the start node, and therefore there's no path. There's no way we can get to our endpoint. So what does this look like on our map of London? Well, you have a really nice kind of effect of adding all the numbers. You can see kind of the wave goes through. And then we've got our final thing there. Can you see that at the back? The color hopefully helps. The numbers are all accurate, I promise. I assume I could add when I made this. So we got to the end, we've given all our scores, and then all we have to do is, that's a 19 for way at the back there. 19 and 2, 21, 2 and 20, 22, so we want to head on there, and we can work all the way back and find our path.
way back?
Yes, it was. It was the quickest way back, given the cost of given the cost of the connections. So it's not the shortest path in terms of connections, but if you look at how much that cost that was. Yeah. So you can see all the way there. We got our shortest path, and that, assuming I measured it vaguely accurately, should be the shortest path to walk from Piccadilly Circus to Nelson's Column. Give it a try. Give me feedback. Sweet. The cool thing about this is, though, that doesn't have to be distance. It's just a number. Those weights, here, it's the distance between 2 points, but there's no reason why that has to just be 100 meters, half a kilometer, anything like that. Instead, imagine we walked each bit of that route and said, this stretch from here to here has a beauty score of 1. It's the most beautiful part. It's the most beautiful any bit of London can get. Or this bit from here to here has a beauty score of 10. You don't want to go there. It's ugly. And instead of finding the shortest path physically between 2 points, you can instead take those scores and figure out the prettiest path between 2 points. Or it's London, it's not Bristol. You might want to take whether something is low crime or high crime and give a score for that stretch of road and avoid all the low crime areas. Or if you're the police, go through all the high crime areas, unless you're feeling a bit lazy today. So in that way, we can just kind of boil down our qualitative world, there we go, into our quantitative world. We don't have to just think in terms of how much will this cost us to walk. We can think of the benefit. And so long as we're saying the least cost is the most desirable aspect of the path between these two nodes, we can use this kind of algorithm to do that. So every time you're typing into Google, I want to go to this place, apart from the fact they're using heavy caching underneath, they're using a similar system to this. They're probably using something a hell of a lot more efficient, but as a start, this is kind of how you can work these things out. We could even use the IMDb ratings for films to find the most quality or least quality distance between two actors, or an actor and Kevin Bacon. We can say, After the Sunset, not that great. I don't know, GoldenEye, and then if we can jump from there. So we can actually just take those scores, and that cost isn't just physical cost, it could be mental cost, or so on. So, special kind of graph, trees. Are we all fans of trees? Yay. Yeah. Thank you. Trees, they're a special kind of graph. We still have nodes, we still have our edges, but we have leaves. So the leaves are, if we start at a root, a hierarchy, we start up here. Leaves are the ones where we've gone as far as we can go away. And one of the cool things about that is there's only one path between two nodes in a tree. If you choose any of those, you'll only ever find one way to get between them. They're acyclic, so you'll never get lost as you go around them. You'll always go through. And the other thing like that, with trees, how many people have, like as a kid, or now if you're not very good at drawing like me, I still start, if I'm going to draw a tree, I draw a Y. And then I take the branches and I turn those into Ys, and I take the branches and turn those into Ys. They're self-similar. So if you look at the small bit, it looks like a Y. If you look at the big bit, it's like a Y, but with lots of fancy bits on it. Trees, just like that. Any bit looks fairly similar to any other bit. And that's one of the great properties of graphs as well. If an approach works on a small graph or a small tree, that same approach will be just as efficient, maybe take a bit longer because you've got more things to process, but it's just as efficient at the macro as it is at the micro. And a tree is basically a forest of trees. You have all these little bits to represent just the one thing. Yeah? So I'm pretty sure we've all used trees before. I'm pretty sure we all have this idea of X belongs to Y belongs to Z. How many people have ever used one of these? This specific kind of calculator. It was great. If you use mechanical keyboards now, this is really hipster. You press the buttons, they go click. It's got red LEDs at the top. It's fantastic. My dad had one. I just like pressing the buttons. But the problem with that is they had a very special way of working. Well, they weren't special at the time. It was the only way to do it at the time. But right now, we type 1 + 1 equals into our calculators, and it just does it. Whereas this one, you had to type in something called reverse Polish notation. You had to type 1, and then a store, and then 1, and then a store, and then plus, and then execute, or something along those lines, which is a bit weird, right? So now, a bit more legacy, I get to tell you about stack arithmetic. So yeah, you type 1 + 2 plus equals instead of 1 + 2 equals. So, stack arithmetic. If you type 1 + 1 into PHP, it will convert that into a tree underneath, into the abstract syntax tree of that expression. And then when you evaluate it, it will do something like this at much lower level, but the general principle remains. So, if you have your reverse notation, 5, 6 + 3 multiply, you start at the front, you treat it as a queue. So you start at the first one, take your 5, put it in your stack. Second one, 6, put it in the stack. You hit an operator. You take the top 2 items, because it's a binary operator, this one, top 2 items from the stack, apply that operation, and then put the result back in the stack. 3 is a number, straight on the stack, multiply, apply it, and then when we've run out of queue, we've either got a stack with 1 item in it, and that's our result, or if we've got more than 1, then we screwed up somewhere, and we've written our notation wrong. The other cool thing about this is there's nothing ambiguous other than the fact that many of us can't read this right now about what that says. We know exactly when to apply plus, we know exactly when to apply multiply. We don't actually have to worry about brackets. If we remember BIDMAS or BODMAS from school, operator precedence stuff, that representation, there's no need for that. It's baked into the way it works. But we can't really read it. Instead, we have to write something like that, and then add brackets, which also isn't that legible, just to get exactly the same result there. So, I mentioned that trees are done underneath in PHP. It constructs an abstract syntax tree. It breaks that down with something called the shunting yard algorithm, or a shunting yard algorithm is one way of doing that for arithmetic. Right now we're using lectures and parsers and fun things to put into the AST, which is special in PHP7 now. Prior to that, it was all regular expressions and horrible things underneath to get this kind of thing to work, but now it's all nice and flash and fancy underneath. And we can take that and we can represent it as, well, our operators are nodes in our tree, and our numbers, our operands, are the leaves, the leaf nodes of that tree. And all we need to do is walk through that tree. And there are 3 kinds of ways of walking through a tree. There's pre-order, in-order, and post-order. So pre-order, it all references when you output or when you pop the value of each node. So pre-order is do the first node you get to, then visit the child, do whatever you need to there, then visit the other child. So imagine left and right. And here, if we start off with plus, we head down all the way around. So node, yes, head to the left, node, output that, head to the left, node, output that, and so on. We hit 5, which is a leaf. We can't go any further from there, so we go back up and go to the next child. Output 7, and back up and so on. And as a result, we get pre-order. I've asked this question a few times. Does anyone know what that's useful for? Because I don't. Sorry? It's not quite the same as doing it in reverse, which is what post order is. So if we go to in order, which is the way that we're used to writing these things, 5 plus 7 times 3 divided by 23 plus 7, we head down and we say, hit the node, but it's got a child, go to its first child, it's a node, head all the way down until we hit a leaf and output that, then backtrack up. So all the way down the outside, 5 plus 7, and so on as we go through. Which still, if we're paying attention, we note that the division and the multiplication will not give us the same kind of thing that we did with our original sum. So we have to add all the brackets again. But we can consider each part of this, each tree, subtree, as we go in, somewhere to add the brackets as we go along. And then post order is the same kind of thing, but instead of outputting the node in the middle or at the beginning, the parent node at the middle or the beginning, we do it at the end. So 5, 7 plus 3 multiply, and so on as we go through. So how do we get to the tree in the first place? Parsers, lexers, Dijkstra, clever guy, shunting yard algorithm kind of does that. But that's with arithmetic. But you can well imagine that when you apply on the array search, you're putting 2 operands in there when you've written in that. Imagine instead of a plus or a multiply there, we've got array search as the name of the operator, and then underneath we've got whatever expression goes into the first argument is a child, whatever goes into the second argument is a child, and so on as you walk through. Another one, nested sets. How many people know what nested sets are? Cool. Do you know how they work? Cool. Okay. So, the problem, how do you store a tree in a database? Well, you use a GraphDB like Neo4j, and you just throw it all in. It works. Not really. We're scared of change. How do you put it into an RDBMS? Has everyone here ever stored a hierarchical menu for a website? Now you got your top level nav, and then your sub nav, and your sub nav, and all the sections. Cool. So this is home, and this is contact us and about, and this is email form, and so on as we go through. Well, each record has an ID, and each record has a parent ID, right? So our root, the one at the top, doesn't have a parent ID. Everything else says the parent ID of this one is this one's ID, the parent ID of this one is this one's ID, and so on. Cool. That works. We can store that. We can insert. We can remove. It's easy enough to do. So how do you find all of these children or all of these children of this node or this node and so on in an RDBMS when we've set up like that, when we've got parent and an ID? Cool. We get that node's ID, find all those records with that parent ID. Then for those ones there, we find all the records with that as a parent ID, and then we've got to go to the other one and we've got to find all the records for that, and lots of queries and lots of things to do. It's not very efficient. We've got lots of selects just to build our lovely menu for our website, and yeah, we can cache it, but that's cheating because I'm giving you an example. So huge numbers of queries, slow down your website, etc. A better way of doing it is nested sets. We just add 2 more columns to our records. We add a left column and a right column. Each item in our menu has a left value and a right value. And so, if we want to take that tree as we've got connected and put it all in one go, we can take our walking kind of concept, or stepping through everything and walking down, and start assigning those left and right values as we go through. So we start at 0, and we're going to have 1 counter as we go through. We start with our root node at the top here, and we give that a left value of 0. And then as we step down, if we're stepping into a node for the first time, we set the left value to the next value in our counter. So 0, then we get down to this one here, it's 1, 2. And then when we have to leave a node, we're never going to visit any more children, we're in a leaf, etc. We set its right value to our counter as it goes up. So we're at 2, we've got nowhere else to go unless we go back up our tree. 2 and 1 is 3 because we're counting, and so on. And we can go all the way around. And the interesting thing about this is now each one of these children's left and right numbers are between the left and right numbers of the parent. Can I see that? So we've got 0 and 17 for the root. All these numbers here are in. This is a better way of viewing it. This is why it's called nested sets and not nested trees. But this is a similar kind of example. If you imagine electronics is our root, it encompasses everything underneath it. It encompasses everything. Televisions encompass tube, LCD, plasma, LED. I don't know when this was written. This, I just grabbed it off the internet. So there's plenty more under electronics at the moment. But you can see that as kind of, well, I find it fascinating. If you imagine that you're looking at the tree in 3 dimensions and then you just look at it from the top, you get a vague clue as to the structure in sets. Maybe it's just me. The classic way of showing it with sets is to start your counter at 0 on the left-hand side, and every time you start entering a set, bump that up, and every time you leave a set, bump it up. So you've got lefts and rights all the way through. So we might start at 0 and end at 17 and then 1 and so on as we go through. The cool thing about this is just to get all the children of this node here, we need to do a single select from our database, which we could have done with our parent ID, but we can get all of these in one go as children of this one here just by saying, can I get everything with a left greater than my left and a right less than my right, and so on. And if we want to do an insertion in that, we don't have to read the whole tree out as we do. We just have to find the place we're going to put it in, grab its left value, insert our new node, give it a left value of 1 more than the node that we're attaching it to's value, give its right 1 more than that, and then update everything by 2 that's on the right-hand side of that in our tree. So you can see just a single, just a couple of updates and an insert, and we've got that tree and preserve that tree as we go there. And delete is similar as we go through. We just subtract our numbers from our left and right as we're taking stuff out. So if you want to do this in your database abstraction layer in Doctrine, which lots of us will use, Eloquent or Propel, then there are already plugins, behaviors, they used to be called for Doctrine, I can't remember what they're called at the moment, but plugins for that, they'll actually do this for you, but that's how they work underneath. Yes?
Can you get just the children rather than the grandchildren as well?
Yes, because you're storing the parent ID along with the left and right, and so you can just select on there, if that's the kind of thing that you're after. I wish I'd thought of that, but I did. Very quickly just then. Final one, before I bored you to tears with graphs, modeling language. So, one of my favorite things about graphs is a toy that you can build in half an hour if you got your ideas on this, and it encompasses things called Markov chains in graph form. And one thing we can do is we can take sentences and we can convert them to graphs. This is a graph that's very one-directional. We've got a few nodes that are the words, and we know that cat can follow the, and sat can follow cat, and on can follow sat, and the, and so on. We can just take our sentence and convert it like that. Our words are nodes, and if a word can follow another word, then we know that there's a connection, a unidirectional connection from the word at the front to the next word along. If we add in a start node and an end node, you can see that, you know, if we have kind of these null ideas of start and end, then we have a little graph that says, if we walk all the way through this, we'll reproduce the sentence we already have. Yeah, we start at our start node, we walk through, and we can output the cat sat on the mat, hit the end. We've done our depth first search. If we take another sentence and layer that in, the dog sat on the rug, you can see we've got a couple of new words. We've got dog and rug, and for the purposes of presenting, I've separated capital the and lowercase the, but we can work on that. We layer that in, we can say dog now with our new sentence can follow the, and then sat can follow dog, and then rug can follow the, and rug can end the sentence. Now imagine doing that with lots of sentences and building up a huge graph. What we can then do is say, just walk it randomly. So if we start at our start node, the can start a sentence. We then say, well, we've got 2 paths out of the in this graph, so let's randomly choose dog. Cool. Only one way out of dog, sat. Then sat on the, got another random choice here, mat. We've chosen that. And we hit the end, and we've generated a new sentence that we didn't put in. It makes sense in this example. Quite often it'll be gibberish, but it's grammatically sound. And in taking this approach, the graph is actually modeled grammar. English, yeah, it's not fantastic. Something a bit more structured, like Latin, might be a bit better, but you can see how doing this several times, we can actually start walking this graph that we build up of loads of input and generate novel sentences. So I've been doing this for years, just on and off. It doesn't take very long to build. And one day I thought, what kind of input can I put in? I know. So if you've got your phones, you check this out live if it's not going to crash. If you go to choult.com/DM, you will find the Daily Mail headline generator, which will give you a real Daily Mail headline and a randomly generated one with the technique I've just shown you. And sometimes it will be absolute gibberish and easy to do, but every now and then it sounds like something the Daily Mail would write. So for example, North Korea fires a 60-foot well in the first job, says he was shot dead, his emotional visit to long-forgotten 1846 Wild West settlers who won by ISIS attack. It could have been written by them. It's random, but you know, sometimes they go on and on. Then you get the emotional stories. Michael Phelps gets his friend's Japanese Akita dog. Aww, isn't that cute? My favorite are the inspirational ones. The awe-inspiring moment. America's Got Talent act goes gluten-free with her brother. It's all randomly generated, but you can see, hopefully on your phones right now, how you can just chuck all this random stuff in, get some random gobbledygook out, but sometimes it makes sense and other times a bit less sense. Just like the Daily Mail. Or if your politics are different to mine, The Guardian. So, in summary, graphs are cool. Thanks. I think we've got time for a couple of questions. So, anyone got any questions about how awesome graphs are?
Yeah, I was wondering when you said there were plugins for the RMDBS bit, did you mean you can chuck in a table that's just got hierarchical parent stuff and it will do the left-right voids?
Yes, you've got to set up with some of the schema, but it will manage inserting nodes and retrieving nodes for you. So you can say, get me all the children of this, or the antecedents, or just the children of a particular node, and it'll bring it all out in one thing. It'll, if you insert a new node on an old one, it'll know how to update everything else and keep it all in check. And it just does it a lot more efficiently than the standard kind of parent node, child node kind of concept with just a couple of IDs.
If you were creating a chatbot, would it make more sense to do it all in Latin and then run it through like Google Translate?
Maybe. That's a good experiment to give it a go. I'm not sure how well chatbots would do in Latin versus having, versus English that makes sense these days, but it's worth a try. One of the things I want to try and do is take that technique amongst a few others, apply some machine learning to maybe 100 randomly generated titles and figure out how to generate talk titles that are most likely to get 5-star ratings on Joined In. And then I can go from there, pick out the topics from that, and generate random abstracts. And from that, I can pick out, randomly generate a talk. That's my ultimate goal, to take over the conference world, to hack conferences with this kind of stuff. It's pie in the sky, and it's utterly insane, but I might give it a go.
I look forward to hearing that talk.
Anyone else? Cool. So, thank you very much. If you've been affected by any of the talks, any of the issues in this talk, please do drop me a line. Scan the QR code, go and join in, leave me some feedback. As they were saying, I don't know if I've done well, because you might just be British and polite and sat in the audience and going. No, I'm only half British. So please do let me know what you think. If you didn't enjoy it, still give it 5 stars, because then at least I can feel good about the things you say. But seriously, I can't grow without that kind of stuff. Also, please do approach me later. I look like this.
Thanks very much.